In this demonstration, I'm going to talk about moving from mined data to making useful predictions. The idea is to look at a predictive analytics demonstration. I'm going to talk about what it means to move from the descriptive analytics side of information, where we look at the question, what happened? Through this Gartner chart, through the diagnostic analytics section, why did it happen? To the point where we're making predictive analytics. What will happen? Can we use the data set that we currently have, the existing enterprise data, to make predictions about what will come in the future? The data set that I'm going to be looking at is a publicly available data set from the city of Los Angeles, California. This is their livable and sustainable city data set, where they've listed the water and electric usage from the 2005 to 2013. The water usage, measured in hundreds of cubic feet, is given for these 134 zip codes, as well as power usage in kilowatt hours. This is a monthly data set, so I don't have details on during each month, but I have overall what's happened in each one of these area codes from this time block. So the first step is to do descriptive analytics. What did happen? Answer the question, what has happened in the past. So what I've done is made an animation of both the water and the power usage for these 134 zip codes during this time block. So what I'm going to show is a time lapse. On the left hand side in the yellow is the power data, on the right hand side in blue is the water use data. And we're going to step through each month, about 10 months in a second, so doing the entire time is only going to take about 10 seconds. But watching the use, I can see that there are patterns. The data seem to be breathing, that there's peaks and decreases, ups and downs in the usage of the data, and the usage of both power and water. And these are annual cycles. I can move even beyond descriptive analytics to diagnostic analytics just with this data set alone, where instead of plotting just individual zip codes, I aggregate the entire data set and look at data usage per month over this entire 6 or 7 year time window. And what I can see is that there are repeatable patterns. Year in and year out, the water usage goes up in the months of July, August, and September, which correspond to summer irrigation. And these are the dry months in Los Angeles, where people need to use water for irrigating yards and crops. Similarly, there are patterns in the power data, both in terms of July-August, where the temperatures are highest and the need to use power for air conditioning is the greatest, as well as in January, where it gets a little cooler in Los Angeles and there's a need for a little bit more power in order to do winter heating. But moving beyond diagnostic analytics, we want to really get to predictive analytics. Can we take the previous usage? On the left is the total water use, and on the right is the total power use. And I've just chopped off the last 11 months of each of these two data sets, and on this plot they're shown in the dashed line as opposed to the solid line. What I want to be able to do is to taking the previous data, the data up to and before these last 11 months, can I predict what will happen? And one of the reasons I want to predict what will happen is in order to optimize the usage of these resources. So both the water and the power, I'm imagining, are coming from external suppliers, and these suppliers I need to have some idea how much how much we're going to purchase from them, and then we'll supply both the power and the water to our customers. In an ideal world, we make a perfect prediction, and we just move those resources from the supplier to the customers, and everybody's happy. However, if we overpredict, we order too much from the supplier. Both water and power are somewhat temporary resources, and what will end up happening is that the amount that we've overpredicted and we've purchased too much from the supplier is just going to end up at waste. I'm considering a world in which the water is just going down the drain and the power is just going out as heat. So there's no recovery from these products if we overpredict and order too much from the supplier. Similarly, if we underpredict, we're going to have lost income. We don't have enough power or water for the customers who've demanded it, and they're going to end up with water shortages, rationing, burnt lawns, or in the case of power, rolling brownouts or rolling blackouts, and customers who are too hot and unhappy with us. So in either of these cases, I'm going to consider a model in which they're equally bad. Both over-predicting and under-predicting lead to the same penalty. However, I'm not dealing with just a single supplier and a single customer. I have this network of locations where I have all these different zip codes. And I could consider a situation where if I purchase from the supplier an overall amount for my network, that I could redistribute some of those resources in and among the network. So if I have too much power in one location, I could move it to the other location, similarly with water. And in this case, overpredicting and underpredicting both lead to waste and the cost of redistributing the resources. So perhaps I'm over or underpredicting the loads on my network, on the power substations or on the water transfer pipes, is more than they can handle, and that would lead to wastes or costs of redistributing the power in among the network. So what I'd like to predict then is, if for each month, what will be the net need for the entire network, so how much should I purchase from the supplier, as well as what's going to be the need for each location in my network so that I can distribute those supplies, the power and the water, appropriately so that customers are optimally happy. We want to reach that green line where we've matched the customer need. I'm going to compare my machine learning models, my predictive analytics, with a very simple model. And this is I'm calling use last year's numbers model. As a teenager working in a restaurant, we wanted to have a prediction of how much food to prepare for a given evening. And the model that we used was to use the same number from last week. So Friday night, we were looking for a Friday night crowd or a Saturday night crowd. And we'd modify those numbers a little bit depending on the special occasions, holiday weekends, or other events happening. But for the most part, we used last week's number as the model for predicting what would happen this week. So what if the power company and the water company did the same thing? So I'm going to start looking at the water usage. And this is what it would look like if the water company used the 2010, it looks like a July 2010 number, and make that prediction. You can see the prediction's a little bit high, what actually happens in 2011. So I add up all of those predictions for all the months, and what I'm showing here is a couple of things simultaneously on this plot. The blue are over predictions. Those are the total amount where I've over predicted for each of the locations. And the yellow correspond to under predictions, where I've predicted too little water for compared to what the locations actually used. And then the red bar is the net of those two. So that the red bar, if it lands on 0, that means that whatever I overpredicted for some places and underpredicted for other places, they add up to 0, and I can handle the difference just using redistribution of resources within my network. And you can see that the used last year's number model doesn't perform very well. That we overpredicted just a little bit in August 2011, but then we went through a large period of time, December through May, where we've seriously underpredicted what gets used by the actual network, the actual customers. I add up the net errors, all the red lines, and I end up with a minus 826 HCF of water. And so that seems like a fairly large number, but the total volume is 42,000 HCF. And so it turns out it's only a 2% error. I'm only off by 2% of my total. My predictions are fairly close, within 2%, using this very simple last year's number model. I can also look at the total local prediction error. So each one of the gray lines in the chart on the right corresponds to a zip code. And so I'm plotting the discrepancy between my prediction and what actually happened. If I overpredict, it's a positive number, and if I underpredict, it's a negative number. And then I add up all the times when I'm off, all the times when I'm wrong. And it doesn't matter if I'm positive or negative, I'm adding up the absolute value. And I end up with 2,600 or so HCF of resources that I'm wrong on and would require redistribution. So this gives me an idea of what the redistribution load would be. And again, it's only about 6% of the total volume for all of the zip codes for the water. This is a baseline. This is a very simple model, doesn't require machine learning, doesn't require computers, just look at last year's number and move forward with that. The next step is to do a slightly more complicated linear model, where I not only take into account last year's number, but also last month's number. I also do a running average from the last few years, and I also look at a running average from the last few months. I put all those together and do a simple linear regression, and I get slightly better predictions. My total error is down from about 800 to about 600 HCF. So I've reduced the amount of total waste, or in this case, under predictions, for this 11-month period, as well as my local predictions are slightly better, from 2,600 total to about 2,100. So I've reduced the amount of local redistribution that would be needed on this network. And this is only using just the raw data set. So I can do a little bit better by using a very simple machine learning algorithm. But I can do even better than that by data enriching. So I'm going to draw data from 3 outside sources. The first source is the US Census from the 2010 census. This gives me information about the population of each zip code. This is not something that necessarily changes month to month or even year to year, but it gives me an idea of how many people live in each zip code, and it better enables a prediction of the water use for those zip codes. The second data is from the IRS. They have publicly available income tax returns in aggregate for each zip code. And from that I'm pulling both the adjusted gross income as well as salary and wages. And I pull one other feature. I pull the earned income credit usage for each zip code from the IRS data. The third data set I take from NOAA as the weather record. Because all of these zip codes are all essentially in the same geographical location, I just pull the weather from the Los Angeles International Airport for this period of time, for these 6 or 7 years. And I measure precipitation, average temperature, wind speed, the heating degree days, and cooling degree days. And those are all data that come from the National Oceanic and Atmospheric Administration. I join all those data back together with the data that comes from the customer itself, the supplier itself, the LA's water and power use organizations. So to compare to the linear model, this is just going back 2 slides. The linear model had a performance of minus about 570 HCF total and a local prediction of error of about 2,100 HCF. And when I add these extra data pieces from the data enriched model, as well as using an adaptive approach where after each month I go back and I repredict using the previous month's data, which I didn't do in the linear model and doesn't make sense to do and use last year's data model. So the combination of both of these mean that the net result of my predictions is now down to about 460 under predict 460 HCF on the total volume. So I've cut my total error by about half, as well as my local prediction error, which also improved a little bit over the linear model. So I have less redistribution to do inside the network. I can do the same thing with the power data. This is what the base last year model looks like for power data, where the total error for the 11 months is about an under prediction of about 22,000 kilowatt hours. But the volume is significantly higher, 687,000 kilowatt hours, so my under prediction is only about 3%. And the local redistribution error is about 51,000, maybe 52,000, which is significantly larger relatively. It's about 7.5% error compared to the errors in the water redistribution numbers, which weren't nearly as bad. And then when I apply the machine learning, the adaptive data enriched model, I bring down the total error, the net error, to only about 3,000 kilowatt hours, or only about a 0.5% on the total volume. So I can do significantly better in terms of predicting the power use of the coming months using this adaptive machine learning model. As well, the local prediction error also significantly improves from an error of about 7% down to about 4%. And the presence of the dark black line in the middle indicates that most of the predictions are about right on for these zip codes. There's a bonus that comes out of doing this type of machine learning, and that's that I can return back to diagnostic analytics. The machine learning algorithms not only tell me what the predictions are, but because I'm using a boosted decision tree algorithm, I also get which variables were most important in making those predictions. And so I've listed on the left the power, or the left is the water and the right is the power predictions. These are the most important variables in order of importance. The ones that are uncolored come from the base set. These are the prior month or the prior year numbers. The green highlighted numbers come from the IRS data. And on the left we see that the next most important variable is the level of earned income credit usage in a particular geography, as well as the cooling degree days, the adjusted gross income, and the number of tax returns, which is actually a better number for the number of people in a given locale for each year, because the number of tax returns is essentially proportional to the number of people that live in a location, as well as then precipitation, which I think might think that would play a role in predicting the water usage. And on the power usage side, certainly the next most important variable after the base system itself is the number of cooling degree days. That tells the machine learning algorithms how much air conditioning is going to be needed, as well as the number of people, the number of tax returns, and their adjusted gross income. Also says something about a fairly strong indicator of how much power is going to be used. So in summary, this is what I was able to do with the machine learning, making predictive analytics, predictive diagnostics, what will happen as opposed to just looking at what has happened. The water usage, I went from a very simple last year prediction model with a total net error of about negative 800 or under prediction of 800 HCF to a machine learning under prediction of only about 400, an improvement at 45%. The absolute local error was reduced from about 2600 for the simple model to about 1900, an improvement about 26%. And the power usage, the models were both significantly improved from our very simple model. From the total net error was reduced from an under prediction of 22,000 kilowatt hours down to 3,000 kilowatt hours, a whopping 86% improvement. The local error, the redistribution costs would significantly be reduced as well from 51,000 kilowatt hours to down to 30,000 kilowatt hours. So this is an example of one way to use existing enterprise data, which is a fairly simple measurement of what has happened. It's a simple bulk measurement. That I can use that to make improvements in the predictions of what will happen, which will then improve the bottom line because we've improved the purchasing from the supplier as well as reduced network distribution costs or redistribution costs in our and among our locations. Thank you for listening, and if you have questions, comments, or are interested in further conversations, please contact me via LinkedIn. Thank you.